Thank you for joining our final webinar in our four-part Open-NFP fall webinar series. Today, John Sonchack is going to present feature-rich flow monitoring with P4. A copy of the presentation, archive replay, as well as any project code will be made available shortly after the webinar. These, as well as our previous webinars, can be all found on the classroom page on the OpenNFP.org website. John Sonchack is a PhD candidate working in the Distributed Systems Lab at the University of Pennsylvania. His current research focuses on frameworks for packet processing with heterogeneous systems. For today's webinar, flow records provide a detailed and compact view of network traffic, but grouping packets into flow records is complex. It is challenging to leverage high-performance P4 hardware without sacrificing record quality. Today, we introduce a new approach that offers both performance and quality by tightly coupling P4 hardware with CPUs. Before we begin, Open-NFP would like to invite you all to the Data Plane Acceleration Developer Day, or DXDD, which we just announced yesterday, and the first annual DXDD Hackathon on December 11th and 12th in Mountain View, California. The DXDD will bring together researchers, developers, students, and industry affiliates for hands-on training and discussions about recent data plane acceleration developments and future advancement. The extensive hands-on training will include an introduction and advanced topics on OVS, P4, and the NFP architecture, actions in C, as well as new approaches to data plane acceleration such as eBPF. The DXDD Hackathon will bring teams together to push the boundaries of data plane performance and scalability. Participating teams will utilize advanced programmable networking features and optimize performance and scaling for applications. The hackathon competition is open for startups and academics. If you're interested in registering for the DXDD, we'll be offering a special 50% off discount to today's webinar attendees. You can find the discount code in the chat window. This code will expire on Sunday, November 5th. In addition to the discount code, if you refer 3 people to register for the DXDD, your registration fee is on us. We hope to see you all there. Thank you, and over to you, John.
All right, great. Thank you for the introduction. Glad to have some of your time this afternoon to present some of the work we've been doing with P4. And so the topic of this webinar, this presentation, is looking at P4 as a tool that we can use to accelerate flow record monitoring. And so at a high level, there are going to be 3 parts to this presentation. First, we'll talk briefly about flow records, understand why they're useful for monitoring, what their benefits are, and what some of the challenges are in using them. Next, we'll look at the design and implementation of our system that uses P4 hardware to accelerate flow record generation systems. And then finally, we'll look at some benchmarks, kind of evaluating the effectiveness and the performance of our system on real hardware and with real traffic traces. And we'll talk a little bit about some of the optimizations that we use to improve the performance of the actual P4 component on the Metronome NFP SmartNICs. And so the point of talking about the optimizations is they're kind of designed to be portable techniques, so hopefully you'll have some use for them in your own projects. So let's start by talking at a high level about flow records. So a flow record is basically a data format that summarizes a group of packets in the same TCP or UDP stream, usually. And so there are 2 basic parts to a flow record. First, the key of the flow record, which basically just describes which packets the record is summarizing. And second, the features of the flow record. And these are statistics and metadata that summarize those packets in that flow in a number of different dimensions. And this table shows some examples of statistics that some applications may use, but in general, there can be many different features depending on the needs of the application. So what do you actually do with flow records? Well, ultimately flow records are basically input to analysis applications. So there's some monitoring infrastructure on your network that produces these flow records based on the traffic and the links that you're monitoring. And it provides these flow records to analysis applications that kind of go through and analyze the flow records for things like security or traffic management or debugging. And generally, these analysis applications have two goals. Well, they can have many goals, but there are two kind of high-level goals that are common. One is to provide information to network operators, so about the conditions of the network, security threats, and so on. And the second goal is a lot of times these analysis applications make decisions about reconfiguring the network. And so over the last few years, there's been a lot of examples of these types of applications with OpenFlow work. And so those are examples of things that do analysis to make decisions about reconfiguring the network. And so there are a lot of applications, analysis applications, that use flow records. There's some resources here if you're interested in finding more of them. Now, the reason why flow records are kind of widely used from the application perspective is because they're efficient. They reduce the cost of your monitoring infrastructure. So if you look at the size and the rate of flow records that you have to analyze compared to something like packet headers, the volume and the rate of flow records is much lower because flow records are more compact than packet headers, and also because new flow records arrive at the analysis application at the same rate as flows, which arrive orders of magnitude less frequently than packets. And so this efficiency, this reduced cost is important, increasingly important, because as networks kind of become more complex and larger, high coverage monitoring also becomes more important. Today, we're increasingly interested into having visibility into all of the links in our network, right? So if you're a security application, for example, you may want it to be analyzing traffic from the inside of your network, as well as, the outward-facing wide area link. So when you want high coverage, the efficiency of flow records is critical to being able to do that without prohibitive cost. And so an important aspect of flow records is their richness. And so we call this information richness, which basically describes two properties. So first, the accuracy of the flow records. Do the flow records account for every packet and every flow on the links that the monitoring system is actually monitoring? Accuracy is important for application correctness. If you're trying to detect threats and you're feeding your threat detection application flow records that don't actually account for every flow, then you will probably miss something critical, especially if it's like a low-rate attack. The other aspect of information richness is feature richness. So this table on the right shows some example features that a flow record can have. There are basically an infinite number of other features that it could have instead. And different applications require different features. They're able to use them in different ways. So feature richness is important because it determines the effectiveness of your applications. Particularly with a lot of recent machine learning approaches, you can really get a lot out of having kind of different dimensions of the traffic summarized by different features. And so the reason why I talk about flow record richness is if you look at current approaches to monitor the network and produce flow records, you basically have a trade-off between the overhead of the monitoring infrastructure and the information richness of the flow records that it generates. So on one side of the spectrum, you can use software running on commodity servers to generate your flow records. Now, software can generate very rich flow records. You can compute whatever features you want. You don't have to sample to reduce accuracy. But the downside is, if you're doing it in software, there's a lot of overhead. So the individual throughput of a single commodity server running flow record generation software is going to be low relative to kind of the total capacity of your network. And so your monitoring infrastructure is going to need to have a lot of flow record generation hardware. At the other end of the spectrum, there are kind of switch-based techniques, like sampling and dedicated hardware embedded into the switch. And these approaches reduce the overhead of the flow record generation. Sampling accounts for a fraction of the packets on the monitored links. That reduces overhead directly, but it also reduces the accuracy of your flow records because you're not accounting for every packet. Dedicated ASICs don't have to sample, but the problem there is the features of the flows are kind of baked into hardware. And if they're not baked into hardware, they're certainly not something that you as a developer can change. So you're kind of locked into using the fixed feature sets that they're built with, which limits the feature richness. And so our goal in this line of work was to look at combining software flow record generation and the information richness and flexibility that it provides with P4 hardware acceleration that can reduce the overhead of kind of the overall monitoring infrastructure by basically reducing the amount of work that the CPU or the software has to do. So that's kind of a high-level look at flow records and why they're useful and our main goal in this system. Next, let's take a closer look at the actual system that we built to accelerate flow record generation using P4 hardware. So the main idea is that we use P4 hardware to pre-process packets into what we call microflow records. And so the idea of a microflow record is that it basically summarizes a burst of traffic, a burst of packets, rather, within a specific flow. And so the P4 hardware generates these microflow records, and it sends them to software, which aggregates them much in the same way that it would aggregate regular packets into flow records. But the benefit is each microflow record summarizes multiple packets already. There's some aggregation that has already happened. So the overall work of the software is going to be much less. So compared to just processing packets directly. And so we get increased efficiency because of the pre-processing that the P4 hardware is doing, but we also get information richness because we're not sampling to reduce accuracy, and we're still talking about hardware that can be configured basically to produce flow records with whatever features you need. So that's the high-level idea of our system. How do we actually implement this? So as a first attempt, we looked at kind of a open flow type approach where we just use a standard forwarding table to track flows in the P4 hardware. And so the idea here is we have a kind of a standard forwarding table that maps packets to counters or features based on the key. So there's one entry for every currently active flow. And so when packets come in, if there is a record in the forwarding table for that packet's flow, we just increment the counters, update the features. If there's no record, then we send the packet to a control application running on the CPU that inserts a new entry into the forwarding table, and also manages kind of timing out flows when they expire and exporting the actual flow records. So this is kind of a simple approach, and the downside here was the overhead of actually updating the forwarding table. So most P4 hardware, most OpenFlow hardware that from the preceding generation can support relatively low forwarding table update rates. And this is because it's a fairly complex operation. So it depends on the platform, but generally it's something like a few hundred to a few thousand forwarding table updates per second, which is not enough to kind of keep up with the flow arrivals on even 10 gigabit links, for example. So this approach does not work because of the overhead of the interaction between the control process and the forwarding table. So our second design, the one that we ended up using, was designed to kind of keep the CPU process out of the critical path of updating the table that maps keys to flow features. And so the idea is, instead of using a forwarding table, we basically use a flat array in the P4 device that's set up using the registers that we use to store persistent state. And so it's a flat array that we just index based on the hash of the packet's key. So when a packet comes in to the P4 component, the first thing we do is compute the hash of the packet's key, its IP5 tuple, and then we use this hash value to index into a position in our flat array. Now, we load the key that's currently stored at that position, which represents the key of the flow that that slot is tracking. If the keys match, the logic is simple. We just update whatever counters, whatever features we're storing in that slot. The challenge comes in when we get a collision. So when we get a packet that maps to a slot in the array that's currently storing a different flow, what do we do? Collision resolution logic is basically too complex to implement in P4, something like linear probing or chaining. So instead of attempting to do that, we use a very simple heuristic, which is to evict the older record up to the CPU. And so this evicted record is a microflow. The CPU takes that microflow and inserts it into a regular hash table that ultimately aggregates the microflows into complete flow records. And so the benefit is the P4 component can do all of this logic kind of at line rate without needing to invoke the CPU. And the CPU benefits because instead of operating on packets, it's operating on these microflows. And each microflow represents many, ideally many packets. So the overall workload is reduced. So this is a quick look at a simple implementation in P4 of the logic. This will be posted on the repo that I'll link at the end. But basically, it's very simple. We have these registers that are the kind of flat arrays that map packets to microflow records based on a hash of their key. We have the simple control logic that either updates an entry or replaces it with a new entry and sends the old one to the CPU. And we have these actions that actually implement the logic that each table called with these apply functions uses. So that's the high-level idea. Again, we use the P4 hardware to pre-group packets into these microflow records, which reduces the amount of work that the CPU has to do. And we still retain information richness because we're not sampling, and we can configure the P4 software and the regular software to track many different features. So now, finally, let's talk about some benchmarks and optimizations that we did to actually get the P4 component working, specifically on this NFP 4000 platform. So we're going to look at three main questions. The first, how much does the P4 hardware actually reduce the CPU workload? Second, what's the actual maximum throughput of the P4 component? And third, finally, what optimization techniques did we use to achieve a good throughput in the P4 hardware? So first, I think the most important question, how much are we actually reducing the workload of the CPU? To answer this question, we analyzed the number of packets that each microflow represents. And as test traffic, we used core router traces from 10 gigabit links, the CADA traces that I'm sure many of you are familiar with. And so the amount of packets per microflow depends on how much memory you allocate to that table on the P4 device that maps packets to microflow records. The more memory you allocate to it, the less often collisions will happen, and the less often collisions happen, the kind of more packets you aggregate into each microflow. And so we see that for a 10 gigabit link, on average, using about 1 megabyte of memory on the SmartNIC forwarding engine, we can aggregate about 10 packets into each microflow. And so that corresponds to a workload reduction of approximately a factor of 10 for the CPU. Because basically, it's doing the same thing that it would do if it was processing each packet individually, right? It gets a piece of data in and it updates some features, except now instead of operating on packets, it's operating on these microflow records, and there are about 1/10 as many microflow records. And so, for context, what does this actually mean in terms of like real hardware? If we look at the average rate, packet rate and microflow rate on these traces, the average packet rate is about 500,000 packets per second. Now, if we're doing aggregation just using software running on the CPU, the commodity server, we can do about 600,000 packets per second. Now, this is assuming that we're using a Redis key value store to map packets to flow records, and that's the main bottleneck. But that's about enough capacity to handle one 10 gigabit link per core. So we do basically, if we use microflows instead, we do basically the same amount of work per microflow as we did per packet, just operating on those, but we have 10 times fewer microflows, right? The rate of arrival is 1/10. And so basically it scales linearly. We can increase the capacity of our monitoring server to be able to handle about 100 gigabits of aggregate link per core. So the P4 hardware has a very big impact on the CPU in terms of how much it reduces its workload. The other important question is, what's actually the maximum throughput of the P4 component? all that workload reduction is great, but it's not really worth anything if the P4 hardware, for example, could only forward or could only process 100,000 packets per second. So we benchmarked this using on the NFP 4000, and it depends on the number of cores that are enabled, and it also depends on what kinds of optimizations you have. This graph here shows the number of cores, shows throughput with respect to the number of cores you have enabled on the P4 SmartNIC. And it also shows the effect of two different optimizations, which I'll talk about in a little bit. But basically, for context, the takeaway is that we can do about 10 million packets per second on the SmartNIC using all of the cores and our two optimizations, this solid line here, which corresponds to roughly 40 to 80 gigabits of traffic with average-sized packets. So basically, the high-level point here is with these optimizations, we can saturate the link capacity of these SmartNICs, assuming average-sized packets. And so the last question is, what are these optimizations that we're showing here in these different lines? What do we need to do to get this working at these rates? And so I'm going to talk about two optimizations that really made the biggest difference in the performance of our P4 code. And the first optimization is finer grained semaphores. So this line down here shows the performance of the baseline implementation that I showed a few slides back, using kind of the default semaphores. There was a lot of contention. This dashed line shows the performance with our finer grained semaphores. So there's clearly a lot of improvement. So before we talk about semaphores, let's kind of go into a little bit more detail. Do we actually need them? Are there potential race conditions in our code? And the answer is yes, because we have multiple cores on the SmartNIC that are processing different packets, but the cores are all sharing one array that maps keys to features of the flow records. And so we can imagine a scenario where two cores are processing packets from different flows, and the packets happen to have the same hash value. So the two cores need to index into the same slot in the array. So if we imagine it, a possible sequence of operations could be the one depicted here. So first core 1 reads the current key at that index, then core 2 reads the current key at that index. Core 3 makes a decision. It's going to replace this record with a new flow, and so it does that, overwrites it with an entry for this packet. And then the second core makes its decision, but it makes its decision based on the stuff that it read before core number 1 actually did the replace operation. So it does an update operation, which is actually wrong because it's updating something that is no longer the right flow. It would actually need to do a replace. So there's race conditions, and we need semaphores because this is the kind of operation that we want. We want each core to have mutually exclusive access to the slot in the array, or the arrays, that it's updating, right? So core 2 needs to wait until core 1 is done so that it can kind of correctly and atomically update that entire slot in the array. So the kind of out-of-the-box way that you do this in P4 on this device is with these register lock pragmas. And what these do is they give exclusive access to the entire register, or for the entire register. So what that means is basically if core 1 is accessing this register, or all of these registers in this case, it's going to have exclusive access to them. And so that gives us the kind of, that gives us the guarantee that we need. We're not going to have a race condition, but it also means that all of the other cores are going to have to wait, even if they're processing packets that map to completely different positions in the array. So we've basically turned our many-cored machine into something that operates serially, which is why the baseline throughput was so low. So one option for doing this better is we could implement everything in micro C. Because in micro C, you can write a spin lock semaphore that does whatever you want, and you can unlock it or lock it whenever you need. But our goal here was we didn't really want to port the kind of core logic of our application into micro C. So what we tried was instead we wrote a semaphore in micro C, and then we wrote a primitive action that encapsulates that semaphore, the operations on that semaphore, into functions that you can call in P4. So we replaced all of the pragmas that lock across an entire array with calls to these primitive actions that we wrote. So you basically just set the ID of the semaphore that you want to operate on, and then you can lock it or unlock it. So here we lock a single slot, a single entry in the array before we start reading it, and then we release the semaphore when we're done. And the net result is, all of our logic is still in P4, but we get the benefit of having the finer grained semaphores that give us the kind of concurrency without contention that we need to take advantage of all of the cores. So that's the first optimization, and that did a lot for our throughput. Made it basically scale linearly with the number of cores on the device. The second optimization was combining tables. So combining tables is an optimization for the single thread performance. It reduces the number of cycles that you spend processing each individual packet. And so the baseline implementation shown here takes about 5,000 cycles to process a packet. And so when we profiled this initially to kind of look for ways to optimize, we found that each table apply took about 900 cycles. So that's a significant percentage of the cycles that we took in doing this was just from applying different tables. So for example, some tables are very easy to combine together. For instance, the table that computes, or the action that computes the hash value and the action that computes the, that loads the key of that position in the array. We can combine those two actions into one action and then combine the tables that call those actions into a single table. And we get about 900 cycles less per packet. So the kind of takeaway is changing tables using an apply function is roughly as expensive as 5 register read or register writes, like 4 to 5. Those take about 200 cycles each. So it's quite expensive. And so we played around with that a little bit, and it naturally led to the question, well, can we merge all of the tables together and just kind of combine all of these different actions into one action in one table that does all of the processing we need. And the challenge here are the branch operations. So, we write different values back to the microflow table based on whether or not the keys match. Right? If the keys match, we update the entry, we increment the packet count, increment the byte count, and so on. If the keys don't match, then we replace the entry with a new one and send the previous entry up to the CPU. So if we were writing our actions in C, it would be kind of easy to do this, or possible to do this at least, with conditional assignment operations. Right? So the idea here would be we just load, compute the hash of the packet, and load the key from the table, and then compute a flag that tells us whether or not there was a collision, and then write back to the table or the array based on that flag. Right? So if the flag is set, for instance, if there was a collision, then we reset the packet count. If there was not a collision, then we increment the packet count. Now, unfortunately, P4 hardware doesn't generally support conditional assignments. Some devices might. I believe in the current Metronome compiler, you can't write these things, these kind of operations, directly in P4. But what we can do is something similar, which is we can use conditional mask. And so the idea here is we take our conditional flag that indicates whether or not a collision has occurred, we compute the flag as an integer, and then we convert that flag into a mask that is 0 if a collision has occurred, and -1 if a collision has not occurred. And so we can use this mask then to write a line of code that basically writes a value to the key or to whatever part of the hash table that we're updating that depends on whether or not the mask is set. So for instance, if you look at this part where we update the stored packet count, if the collision mask is set, then it's going to be -1. And so this will evaluate to 1, and this side will just drop out, right? So it will just be this value that we're writing back. Similarly, if the collision mask is not set, then this will evaluate to -1. So this whole side of the equation will evaluate to an increment operation, and this side will cancel out. So the benefit there is we're basically doing the same thing as a conditional assignment functionally, but we're encoding it in operations that we can actually do within a P4 function, within a P4 action. So we can encode these operations just as modify fields and register writes in P4. And so back to the high-level point, once we have this technique, we can actually merge all of these tables together into one single action. And so the actual P4 code that does that will be posted on the repo, but the high-level point is we get another large advantage from doing that, and ultimately combining all of these tables together gives us about 20 to 30% better throughput on the P4 device. So those are kind of the three focuses of our benchmarks and optimization. How much does the P4 hardware reduce CPU workload? What is its maximum throughput? And what are the main optimizations we used to get those throughputs? This is a summary of what we talked about today: the benefits of flow records, the challenge of generating them efficiently without sacrificing information richness, and our technique to accelerate software flow record generators with P4 hardware. and the evaluations and optimization techniques that we used, which will hopefully be useful to you in other projects. The code will soon be available at this repository as I kind of clean it up and post it. But thank you very much for your time and attending today.
Okay. Thank you, John. Any questions you'd like to type in? Please type them in and I'll relay them to John here. To get started, would you like to comment on, I know you touched on going into high performance. Would you like to expand on that, how you see this as you increase line rates to 40 gig or even 100 gig, how the design of the node changes or the design of the software changes?
So I think the design of the software doesn't actually change that much because the CPU utilization is so low when you're actually accelerating it by doing this pre-processing. So the question is basically how much P4 hardware do you have? What is its throughput capacity? And so as we saw, there's kind of a lot of capacity on the CPU to keep up with additional load, as long as you have enough P4 hardware to kind of operate on those capacity links.
Okay. Now, do you see, you didn't touch on this in the webinar, but how do you see this fitting, how do you see the northbound side of your system fitting into, say, an existing distributed analysis system or some kind of tool that helps you visualize and analyze data?
Mm-hmm. Yeah, so I think there's two different approaches. So first of all, at a high level, the goal of the system is to export flow records in whatever format your systems need. So you could easily put kind of a wrapper around the high-level interface that exports them in NetFlow format or IPFix format or whatever the applications need. Another question is, where do you actually put the analysis applications? So if you run them on a standalone server independent of the flow record generator, that's one approach, kind of similar to what you would do today. Another approach is, I think it's possible to use some of the spare CPU capacity on these flow monitoring servers that you have now using the P4 acceleration. You can probably put a good deal of the actual analysis kind of directly on the flow generator and do it there to kind of improve the scalability of the overall system.
Okay. I actually have two interesting questions here. Let me read both of them out.
Sure.
Let me read one out and then I'll read the next one out. It seems to me that semaphores might be avoidable altogether. What if each core would have a separate table? Then there would be no contention, but the CPU would have to combine the microflow records from the different cores during processing. Have you considered this?
Yes, actually, so we did consider that. I think that might have been the first approach that we went with, just allocating a replicated table for each core. The downside is you kind of need more memory, and the overhead of the semaphores was low enough that didn't really provide a significant improvement for the added complexity of the configuration and of the work that the CPU had to do. That's also an interesting approach because a lot of the P4 hardware has like on-chip per core memory, so it kind of may be possible to take this a step further and have a small aggregation table on chip on the P4 device, then feeding to a second layer also on the P4 device in a larger shared table, and then finally feeding out to the actual software. But that's definitely a useful alternate idea to consider with per core tables instead of semaphores.
Okay. Now, then there's this, I actually have a follow-on, but I'll come back to that. So there's a question on where would flow sampling take place as a net flow?
Where would flow sampling take place as a net flow? So as in a sampling net flow generator where you want to sample flows?
Let's assume that's the question, unless Stephen Monetti wants to clarify it some more.
So I would say that you would sample, due to the kind of efficiency of the CPU component, I think it would make the most sense to sample from the flows that are generated by the CPU. You could probably use some sort of scheme to embed the sampling lower, but it doesn't seem to me that the performance or efficiency benefits would outweigh the complexity. So I would just say the sampling is probably best done on the CPU after the flows are generated, selecting what you actually want to export up to the applications.
Okay. Ingwer and Stephen, I hope your questions were answered. If there are no more questions, I'll hand it over to Brian.
Okay, thank you, Bapi. So this concludes our last webinar of the fall series. And thank you, John, for your presentation. Again, all of this will be posted on the Open-NFP website in the classroom section shortly after this. And we hope that you join us for DXDD and Hackathon. If you'd like to learn more about that, please go to the OpenNFP.org website. Thank you, and we'll talk with you shortly.
Thanks, everyone.